language of algebra, the basic grammar of math. Then we'll use that language to start mapping out space with geometry. From there, we'll zoom right in on the incredible power of triangles, then build some stuff in 3D, and finally, we'll learn how to decode data and understand the odds. Let's get to it. First up, algebra. This is where it all begins. We're laying the foundation stones here. These are the fundamental rules that literally everything else is built on. Check out this first piece of our blueprint. It's all about how numbers play with each other, kind of like these gears meshing together. It says that for any two positive numbers, if you multiply their highest common factor by their lowest common multiple, you get the exact same answer as just multiplying the two numbers together. It's a really elegant, super reliable piece of machinery in our math toolkit. Okay, so moving on from pure numbers, let's see how equations can describe relationships. Here's a simple question. You've got two straight lines on a graph. What can happen? Well, it turns out there are only three possibilities. First, they can cross at one single point, and this formula you see here tells us exactly when that happens. If the ratio of the a's, that's the x coefficients, is different from the ratio of the b's, the y coefficients, then boom, they are guaranteed to intersect at one and only one unique spot. But what if they don't cross? If they're on the same flat plane and they never ever meet, there's really only one thing they can be. They have to be parallel, and the math totally backs this up. This happens when the ratios of the x and y coefficients are equal, but that last ratio, the constant terms, is different. You can think of it like this. They have the exact same slope, they're pointed in the exact same direction, but they start at different places. So they'll run alongside each other forever, but never actually touch. So what's our third and final possibility? Now this one's a little tricky, because things aren't always what they seem. What if you have two equations that look totally different, but they're actually the same line in disguise? This is what happens when all the ratios are equal. The x's, the y's, and the constants. It just means that every single point on one line is also on the other line. They're basically lying right on top of each other. We call them coincident lines, and that gives us infinite solutions. Straight lines are great and all, but let's be real, the world is full of curves. Think about the arc of a basketball shot, or the shape of a satellite dish. How does our blueprint handle those? Well, for that, we use something called a quadratic equation. Anytime you see that little x squared term, you know you're not dealing with a straight line anymore. Nope, you're dealing with a smooth, symmetrical curve we call a parabola. So how do we figure out the exact points where that curve crosses our x-axis? For that, we bring out the big guns, the quadratic formula. I know, it might look a little intimidating, but it's the master key. You just plug in your a, b, and c values from the equation, and it spits out the solutions. And see that little part under the square root? That's the discriminant. It even gives you a sneak peek, telling you if you're going to find two solutions, just one, or maybe none at all. Pretty cool, right? Okay, we've built our algebraic foundation. Now, let's use it to actually map the world around us. Welcome to coordinate geometry, where numbers become real positions on a grid. This formula right here is one of the most useful things you'll ever see. It's basically the Pythagorean theorem just dressed up for a coordinate plane. If you have any 2 points on a map, any 2 points at all, you can use this formula to find the exact straight line distance between them. This is the engine behind every GPS system on the planet. Now beyond coordinates, our blueprint has some essential truths about shapes just built into it. For example, Thales' theorem shows us this neat trick with triangles. If you draw a line parallel to one side, it automatically divides the other two sides in perfect proportion. Similarity ratios? Those let us scale any shape up or down while keeping everything looking right. And tangent properties, well, they define that elegant way a straight line can just kiss the edge of a circle at exactly one point. Alright, let's zoom in on one shape in particular, the triangle. This simple shape is so ridiculously important that it gets its very own branch of mathematics, trigonometry, which is really just the measurement of triangles. You know, the heart of trigonometry is incredibly simple. It all boils down to three key ratios: sine, cosine, and tangent. And what's so amazing is that for any right-angle triangle, if you know just one of the angles, these ratios give you the exact relationship between the lengths of all the sides. This one simple idea is the foundation for everything, from building skyscrapers to mapping the stars. And while those ratios work for any angle, think of this table as your ultimate cheat sheet. It gives you the must-know values for the most common angles we find out in the real world: 30, 45, and 60 degrees. Seriously, these are the numbers that engineers and physicists have practically tattooed on their brains, and they are incredibly useful shortcuts. Okay, so we've pretty much mastered flat, two-dimensional shapes, but we live in a three-dimensional world, right? So let's expand our blueprint to account for things like volume and surface area. This table is basically our architectural guide. Need to know how much paint it'll take to cover a cylindrical tank? Yep, use the formula for total surface area. Want to figure out how much sheet metal you need for a cone-shaped funnel? It's right there. These formulas let us measure the skin of the most common 3D solids we run into every day. For our final section, we're going to move away from the certainties of perfect shapes and lines and into the world of uncertainty. How can our blueprint help us make sense of messy data and maybe even predict the future? So when you're faced with just a huge pile of data, the first thing you want to know is, what's typical here? What's the center? These three tools help us answer that. The mean is just the good old average. The median is the value smack dab in the middle when you line everything up. And the mode is simply the one that shows up most often. Each one gives us a slightly different snapshot of the data's center. And now, for something that is just so cool. You'd never think these three different measurements would be related, but a lot of the time, they are. For many data sets, this empirical formula gives us a surprisingly accurate relationship between the mean, the median, and the mode. It's just a beautiful little piece of mathematical elegance connecting them all. So